Most reinforcement learning agents learn the hard way by pure trial and error. They stumble around, try millions of actions, and slowly memorize what tends to pay off. That works, but it is painfully slow, and it can be dangerous. Imagine crashing a real robot 10,000 times just to learn to walk. So what if the agent could build a little model of how its world works, and then think ahead, imagining the consequences of actions before committing to them? That single shift is the whole idea behind model-based reinforcement learning, and it changes the economics of learning completely. Let's dig in. First, let's see the two philosophies side by side. Here, the agent skips any model of the world entirely. It learns values or a policy directly from real experience, one hard-won interaction at a time. Q learning and policy gradients live in this camp. This is robust and refreshingly simple, but it can be brutally sample-hungry because every single thing it learns has to come from actually doing it out in the real environment. This approach flips that around. The agent first learns a model of how the environment behaves, and then uses it to plan, imagining possible futures internally before it acts. Instead of only reacting from memorized values, it can genuinely look ahead. The environment becomes something it understands well enough to simulate in its head, not just something it blindly reacts to. So how does an agent actually pull this off? Walk the loop one step at a time. It starts by learning a model. From its experience, the agent trains something that predicts two things: given a state and an action, what the next state will be, and what reward it will receive. This learned model is a compressed, queryable version of the environment's dynamics. With that model in hand, the agent can simulate. It rolls out imagined futures entirely in its head, asking what would happen if I did this, then this, without ever touching the real world. These rollouts are fast and cheap compared to real interaction, so it can run enormous numbers of them. Now it can plan or train on that imagined experience. It might search through possible action sequences, the way Monte Carlo tree search does, or generate mountains of synthetic data to train a policy on. Either way, most of the hard thinking happens inside the model rather than in reality. Finally, the agent acts in the real environment, and because so much of the learning already happened in imagination, it needs far fewer real interactions to reach strong performance. That sample efficiency is the entire payoff, and it's why these methods shine wherever real experience is slow, costly, or genuinely risky. Boil it down, and 3 ideas define model-based reinforcement learning. It learns a predictive model of the environment. That model captures the dynamics, how states transition, and where reward comes from, turning the world into something the agent can query and reason about rather than merely react to. It plans or imagines to gain sample efficiency. By generating cheap, simulated experience and looking ahead inside the model, it can learn strong behavior from far fewer real interactions than a model-free method would ever need. It powers some of the field's most striking results, but carries a catch. MuZero masters board games and Atari by learning a model and planning, and Dreamer trains entirely inside its own imagined world. The danger is model error, since a planner can exploit inaccuracies, confidently choosing actions that look great in the flawed model, but fail in reality. All right, let's lock in the essentials. This approach has the agent learn a model of how its environment works, then plan or imagine inside it rather than relying only on trial and error. The model predicts the next state and the reward, letting the agent look ahead and simulate possible futures before it ever acts. Its headline advantage is sample efficiency, needing far fewer real interactions, which matters when experience is slow, expensive, or risky, as with robots and self-driving. It powers MuZero and Dreamer, though model error remains the central challenge to manage. If learning how intelligent agents actually think appeals to you, we unpack a lot more of it over at standardy.com. See you inside.